Today's topic is fundamental concept of voltage regulator. That what we mean by regulation. This is an AC which is to be rectified and to be regulated, and then it is given to a transformer and rectifier. Then it is given to a filter circuit for eliminating the ripples. Then we having a voltage regulator. Then it is the output. Output is drawn here across the load. Here it is rectified, then smoothing, then regulation. Regulation means totally constant voltage. Total constant, exactly constant, irrespective of the variation in input voltage and the variation of the load resistance. Here is a generator as a regulator. Nowadays no one is using simple the generator as a regulator. Nowadays IC is used. IC is used, okay? But this is a basic generator which acts as a regulator. So this is N section of generator which is applied to a positive supply, and it is a P section. Okay. Now this is a series resistor. Now here the output resistance, which is a variable RL. So this is a supply input voltage, variation in the magnitude of the input voltage. The output remain constant, first of all. And second, if the input is constant and the load is variable, mean load resistance is variable, even then the output remain constant. So this is how the generator acts. Voltage regulators. Nowadays, the generator regulator is not much in use, and IC integrated circuits are used for the voltage regulations. There are many advantages of the IC regulators, like it is in use, small in size, cost is very less, versatile, and etc. etc. There are many applications of IC regulators over the generator regulator. Like the fixed voltage regulator, they provide the fixed output voltage, like 7805. It gives 5 volt output, and it is in a series, 78 series. It provides us the positive voltage. Like 7805 provides 5 volts, 7806 it provides us 6 volt positive voltage, 7809 it provides us the 9 volt positive voltage. Okay, and there are negative voltage regulator. It is 79 series. 79 series provides us the output voltage which is negative. 7905 it gives 5 volts negative supply output. 7906 it provides the 6 volt negative output. This is 79 series. There's an adjustable voltage regulator where the output voltage, which is regulated voltage, can be varied. And there is an IC LM317 where it provides us regulated positive voltage, which is adjustable and can be varied over a range 1.2 volts to 57 volt. And there is another IC LM317. It provides us a negative voltage which can also be varied. And actually LM317 is the complement of LM317. They are similar in design, the only difference being the polarity, because LM317 it gives us negative adjustable voltage, whereas LM317 it gives us positive adjustable voltage. A typical 78 series IC is shown in the figure, and 7805, 7806, 050608, it implies the output which is positive, and like 05 it gives us 5 volt positive voltage, and so on. Regulator classification. There are two types of regulators: series regulators and the shunt regulators. You know what's the difference between the two? In case of series regulators, here there is a control element which is used in series regulator. Control element like a transistor, and it is connected in series with the given load. If with the load the control element is in series, it is called series regulator. And if the control element connected, it is in parallel with the load, then it is called the shunt regulator. Shunt means the control element is in parallel with the load. And the example is Zener diode is an example of the shunt regulator, because the Zener is always connected in parallel with the load. Okay. Factor affecting the voltage regulation. Factor affecting the voltage regulation. What are the different factors? Let's discuss the different factor which affects the voltage regulation or the regulated power supply, These are: number one, load current. Mean if we change the load, it may affect the output voltage. Second, input voltage variation. If there is variation in the source, then it affects the output voltage. And last factor is temperature. It also affects the voltage regulation. Let's now, we are going to learn about how the load current, it affects the voltage regulation. So if we are changing the load, with changing the load current will also change. Let the load along x-axis, the load current is increasing, and along y-axis there's a voltage, and ideal power supply voltage remain constant irrespective of the variation in the load current. But the red line, it is for practical power supply output voltage, and it is the voltage coming down because with increasing the load. And when there is a full load, there is a maximum change in the output voltage. And this is delta V, change in the load voltage, change in the output voltage, the delta IL, change in the load current. So here there is a maximum effect, full load. VFL means full load voltage. And what is the load regulation? When there is no load voltage, minus full load voltage. And percentage voltage regulation is when percentage voltage regulation is when the voltage without any load, that means the maximum constant voltage, minus when there is a full load, mean that load which draw the maximum load current. Full load mean that load, that appliances which draw maximum current. That is VFL. VNL mean there is no load is attached. There is no load. It's not drawing any current. There is no load current. Okay. That difference divided by the VFL. VFL means with full load multiplied by 100. That becomes the percentage load regulation. So if the power supply is good, then the numerator will be very less, and ideally this numerator will be 0, because VNL and VFL will be the same for ideal supply. For ideal supply, there is the load regulation, percentage load regulation, it is 0. And if there is some value and if there is more value, that means poor power supply. Line regulation, what we mean by line regulation. This is a rectifier with a filter circuit, and here it is AC is applied to the rectifier, and here we are getting some rectified voltage which is input to the regulator. Input of the regulator is Vin, and it is giving the regulated voltage VL across the load. This is a load which is variable, and there is a load current. So what we mean by line regulation? Line regulation sometimes also called the source regulation. And let the voltage is 220 or 230 volt with 50 Hz frequency, and it is defined as change in the regulated load voltage, mean output voltage, because of the change in the line or the this one, okay, line or the source voltage. But in a specified range, that is 220 plus minus 10%, it is allowed this much change in the source voltage at constant load current. When we are discussing the line regulation, load current should not change. So what is the source voltage regulation? Source regulation, VLH minus VLL upon V normal. VLH mean load voltage with high line voltage. Load voltage with high line voltage. With LL mean load voltage with low line voltage. Mean there is where it is, we are assuming that line voltage is changing, and sometime it is high and sometime it is low. And V normal mean normal load voltage with typical operating condition. So this is how it is defined, the percentage line regulation. Now there is another parameter, ripple rejection. So there may be some ripples here in the input side, and we are expecting the less ripple at the output side. So ripple rejection means ripple content in output to the ripple content in the input. Okay. Because the ripple content in the output or the ripple content in the input, our regulator should be capable of reducing the ripple. That means ripple content should be as low as possible. Ripple rejection is the ability of the regulator to reject or to reduce the ripple present in the input. So our regulator should minimize or reduce the ripple content. Okay, so ripple rejection should be small for better performance. Now, we study what is the effect of temperature. So that is, we define a temperature stability factor ST. When we affect the temperature, then we keep the other parameter constants like IL, load current, and the line voltage or the source voltage should remain constant. Then we define the stability factor. So in the numerator, what is the change in the output voltage per unit change in the temperature, delta V out over delta T. If the temperature changes by delta T, then we have to measure what is the change in output voltage. So then we divide the change in output voltage and with the change in the temperature. So ST should be also very small as possible for better performance. So it is also defined as thermal coefficient of output voltage. It is the ability of the circuit to maintain the constant output, constant output voltage and the least effect of temperature. So if the output remain constant, but really in practice the output voltage always changes. So it is defined as delta V out per unit V out over delta T. Or you can say change in output voltage per unit output voltage per unit change in temperature, maybe in Kelvin or maybe in Celsius. Or for better performance, DC should be as small as possible. Now we learn about the circuit that is linear series regulator. Linear series regulator. This is a source and input voltage, and let it is unregulated supply, DC supply, V input. Here we are having a transistor. Is a series transistor. R1 and R2 are two resistors. Here it is a comparator. There are two inputs to comparator. One from reference voltage and other from the network R1 and R2. This is the series pass transistor, control, and it is also called the controlling element. The transistor is also called controlling element, and voltage across the transistor is automatically adjusted in such a way so as to get the output voltage constant. So the transistor is, it is a variable resistor, and its resistor varies in such a way that output remain constant. This series pass transistor is operated in the active region. So voltage across the transistor, output voltage. Output voltage actually the input voltage minus the voltage which is developed across the transistor. R1 and R2, there's a feedback network, and they provide a voltage proportional to the output voltage, and that voltage is then compared with the reference voltage. Comparator compares the reference voltage with the feedback voltage. Feedback voltage is provided by R1 and R2. And according to the difference, comparator generates a signal, and that signal is applied to the base of the controlling element. So depending upon the value of the control signal, then the transistor adjusts the voltage across itself. If the feedback voltage and the reference voltage they are exactly equal, then comparator will not give any control signal to the series pass transistor. So in this way the output remain constant. If output increases or decreases, feedback signal gives this information to comparator, and accordingly comparator generates the control signal. That control signal adjusts because it is applied to the base of the series pass transistor. So then the voltage across the transistor adjusts itself so as to output remain constant. Series regulator using op amplifier. It is having the 4 parts. Number 1, the reference voltage circuit. Number 2, error amplifier, which is called comparator. Number 3, series pass transistor control element. Number 4, feedback network. So there is AC voltage given to the unregulated DC supply. Now here we are getting some rectified voltage of this type. Then here is a series pass transistor NPN. Then there is a output voltage and a feedback network produces a voltage proportional to the output voltage, that is beta V0 is feedback signal applied to the inverting terminal of op. So Zener diode produces a reference voltage applied to the non-inverting terminal. Then comparator compares the two and produces a control signal V0 dash applied to the base of the transistor. Then transistor adjusts its voltage so as the output voltage remain constant. Let us see how the regulated action takes place. If output voltage Vout increases due to change in the load current, if we change the load resistor RL, then let the output voltage increases. Then what happens? Output, with the increase in output voltage, the feedback signal beta Vout also increases, and it is applied to the negative of the op. So with the reason V0 dash becomes negative, that is, negative signal is applied to the base of NPN transistor. So that means reduction in the base voltage and reduction in base voltage mean because transistor is acting as emitter follower. So with this reason, emitter current also decreases. So this decrease in emitter current, it keeps again the output voltage at the same level as was before. Let by chance, if the output voltage decreases with the change in the value of the RL, then what happens? The feedback signal also decreases, which is beta V0. That means if the negative of the op is at less voltage, then that means the positive of op is at high. That means V0 dash increases. Increase in V0 dash means base current increases, which implies emitter current increases. Increase in emitter current mean again output comes at the same level as was before. Now we will discuss the shunt voltage regulator. Okay. Now why we call it shunt? There's a question. So here is the unregulated DC supply, and then here is a shunt control element. It is called shunt because it comes in parallel with the load. Here it is the output voltage and this is load, and shunt current element, it is in parallel with load. That's why it is called shunt. So this is a sampling network. Output is a part of output is taken to sampling network. Then that output of the sampling network is applied to comparator. One side, other side is the reference voltage. Then comparator, it compares the two. And accordingly it produces the control signal, which is then applied to the shunt control element. Let current I is coming, it is divided into two parts, IS and IL. I is the sum of IS plus IL. Okay, if IL changes, then IS has to change so as to keep the output voltage constant. IL changes because of the load. So to keep the output voltage constant, IS has to change. So depending upon the value of the control signal, the voltage across the control element, which is Vs, it is adjusted. So it is so adjusted so as to keep the output voltage kept constant by adjusting IS. So this is how the shunt voltage regulator works. Now 3-pin voltage regulator. So this is a series pass transistor. This is input, which is unregulated DC voltage supply. And here it is the output voltage, which is regulated DC voltage. This is a network R1 and R2. And here it is an op amplifier. Minus terminal is attached with the R1 R2 network. So here it is a thermal shutdown and current limiting circuit. The output of the op is given to this circuit. Then that signal is given to the series pass transistor. R1 and R2 produces a feedback signal proportional to the output. Internally generated reference voltage is applied to non-inverting terminal. Comparator op is comparator. It compares reference voltage with the feedback voltage, and according to the difference it produces the control signal. That control signal, just after passing through the current limiting circuits, given to the series pass transistor. Series pass transistor acts as a control element, and the voltage is so adjusted over the transistor so as to keep the output voltage remain constant. Okay. Thermal shutdown and current limiting block provides the protection against increased internal temperature of the circuit.